Start recording. Okay, so what I want to do right now is to have a look at logarithmic graphs. Okay, and you've looked previously at exponential graphs, and we've got, if we were to look at a basic exponential graph, then it's shaped like that. Okay, and here's our x and y axis, and if this is, say, the graph of y equals 2 to the power of x, what we have here is a horizontal asymptote at y equals 0, and got a y-intercept at 0, 1. It's a little bit small, isn't it? Okay, and if we were to have, say, one other point on here, say if x equals 2, then our y value would be 2 to the power of 2, which is 4. Okay, now that's an exponential graph. Okay, logarithmic graphs are conveniently reflections in the line y equals x. Okay, so which means that logarithmic graphs and exponential graphs are inverses of each other. We've already seen that with our study in inverses. An inverse function will be a reflection of the original function in the line y equals x, which means that the logarithmic graph would look like that. As you can see, these two are reflections of each other. Now, what's the equation of this function here? Well, if this here is y equals 2 to the x, this function here would be y equals log with the base 2 of x. Remember that our when we're converting from exponentials to logarithms, they're just different representations of the same thing. So x would equal log base 2 of y. So these two equations are equivalent. Of course, what we've graphed here is y equals log base 2 of x. So in other words, if we were to work out the inverse function of this exponential, remember we start by interchanging our x and y, so we'd write it as x equals 2 to the power of y, and then that being written as a log expression or a log equation, y would equal log base 2 of x. Okay, and that's the graph we've got here. So what does that mean? It means we have here our x-intercept would be at 1, 0. And one other point on here, of course, would be our x value of 4 would correspond to a y value of 2, as opposed to this one here, which is x value of 2 and a y value of 4. Okay, what I'd like to look at now is a few examples of how to sketch logarithmic graphs. So what I'm going to do then is to look at some examples that are in the textbook in the yellow one. And the first one that we'll look at is y equals 3 times the natural log of 2x. Okay, ln is the natural logarithm. Another way we could write this is y equals 3 times log base e of 2x. Okay, so they're the same thing. They're interchangeable. Now, you would have noticed on your scientific calculator a button that has ln. You may have thought it was in, but it's an ln, standing for natural logarithm. Okay, with the logarithm with a base e. And e is Euler's number, or Euler's constant, which is an irrational number like pi, 2.718, and so on. Okay, and it'd be worthwhile just finding a YouTube clip just to explain what that is, to give you a bit of an understanding of where it comes from. Okay, so let's look at what we've got here. When we're drawing or sketching logarithmic graphs, it's worthwhile to have a look at what the basic graph is and then seeing how that's changed. So if we look at the basic sketch of y equals log x, okay, it will always have our x-intercept at 1, and there'll be one other point here which would correspond, which is convenient. I mean, obviously there's an infinite number of points here, but a convenient point to use is the base as your x value, so that would be e, and log base e of e is 1. Okay, and if we were to go back up to the top and have a look at this one here, okay, y equals log base 2 of x, a convenient point would be 2, 1. Okay, because log base 2 of 2 is 1. Log base e of e is 1. Okay, so that's just a convenient extra point, because when we're sketching graphs of log functions, we want any intercepts and one other point. Okay, a minimum of 2 points, one of them being an intercept and one of them being another one. Otherwise, we could have 2 intercepts and that'd be enough, or we could have 2 intercepts and one other point. Okay, we also need to show the asymptote. Okay, so there's a vertical asymptote here at x equals 0. So how has this changed? Okay, let's look at what we've got here. There are 2 dilation factors. There's a dilation factor in the y direction and a dilation factor in the x direction. Okay, so the transformations are dilation by factor of 3 parallel to the y-axis, and a dilation by a factor of 1 over 2 parallel to the x-axis. Okay, that's an important thing to remember. Okay, whatever your x variable is being multiplied by, okay, then the dilation factor is 1 over that value. Okay. So then let's continue. How does that affect our points that we have here? It's worthwhile just having a look at our point here. We've got our x-intercept 1, 0. How has that changed? Dilation factor by a factor of 3 parallel to the y-axis means that our y value will be multiplied by 3. Okay, so clearly that's still going to stay as 0, and our x value will be divided by a factor of 1/2, so it goes from 1 to half. The other point that we have here, E1, that's going to move to, let's look, our y value is being multiplied by 3, and our x value will become E over 2. So these are 2 points that lie on the graph of y equals 3 log 2x. We can see here, obviously, our x-intercept is going from 1, 0 to half 0. There is no horizontal shift, so that means our vertical asymptote will remain the same. Okay, so still got here vertical asymptote x equals 0, and x-intercept is now at a half, and we've got this other point here which is going to be e over 2, 3.